Now we turn our attention to tangent planes. So this problem is analogous to finding the tangent line of a curve at a point, finding tangent plane to a surface at a point. Now, in the plane, there can only be a single tangent line to a curve at any given point. However, in 3 dimensions, there can be many tangent lines of a surface at any given point. If these lines happen to all lie in the exact same plane, then they determine the tangent plane at that point. So let P naught be any point on a surface S, and let C be any curve passing through the point P naught and lying entirely in S. If the tangent lines to all such curves C at P naught lie in the same plane, then this plane is called the tangent plane to S at P naught. And here we can see a picture representation. So here's our surface S. Here is our curve C, passes through x naught, y naught. Here's another one. So here is a tangent line to the red one. Here's a tangent line to the green one. And we can keep going. And you'll notice that this plane will contain all of said tangent lines. So to find the equation of the tangent plane, it is represented by the intersection S with the vertical trace x equals x naught. And this is represented by z equals f of x naught y naught plus f sub y. And remember, this means the partial of f with respect to y at x naught y naught times y minus y naught. Similarly, the equation of the tangent line to the curve that is represented by the intersection S with the vertical trace given by y equals y naught is z equals f of x naught y naught plus the partial of f with respect to x times x naught y naught times x minus x naught. Now, a parallel vector to the first tangent line is j hat plus f sub y x naught y naught k hat. And a parallel vector to the second tangent line is b is I hat plus f sub x at x naught y naught k hat. Since both of these lie in the tangent plane, a normal vector to the tangent plane would thus be given by the cross product. So if you take A cross B, we wind up with f sub x of x naught y naught I hat plus f sub y of x naught y naught j hat minus k hat. So the equation of the tangent plane at the point x naught y naught f of x naught y naught is given by this vector dotted with x minus x naught, y minus y naught, z minus f of x naught y naught is equal to 0. Carrying this through, we find f sub x of x naught y naught times x minus x naught plus f sub y of x naught y naught times y minus y naught minus z minus f of x naught y naught is equal to 0. And if we solve this equation for z, we get our equation. So let S be a surface defined by a differential function, z equals f of xy, and let P naught equal x naught y naught be a point in the domain of f. Then the equation of the tangent plane to S at P naught is given by z is equal to f of x naught y naught plus f sub x of x naught y naught times x minus x naught plus f sub y of x naught y naught times y minus y naught. So let's actually find a tangent plane. So we're going to find the tangent plane to the surface sine 2x cosine 3y at the point pi over 3, pi over 4. So the first thing we're going to want is f of pi over 3 pi over 4. So we'll have sine of 2 pi over 3 times the cosine of 3 pi over 4. So this is the square root of 3 over 2 times negative square root of 2 over 2. So we get negative square root of 6 over 4. Now we want to evaluate both partial derivatives at this point. So first we need f sub x. Well, this is just going to be 2 times the cosine of 2x times the cosine of 3y. And so evaluated at pi over 3 comma pi over 4, 2 cosine of 2 pi over 3 times the cosine of 3 pi over 4. So 2 times negative 1/2 times negative square root of 2 over 2. This will give us the square root of 2 over 2. Next we need f sub y at that point. So the partial with respect to y will be negative 3 sine 2x sine 3y. So now evaluated at pi over 3 pi over 4, negative 3 sine of 2 pi over 3 times the sine of 3 pi over 4. So we get negative 3 times the square root of 3 over 2 times the square root of 2 over 2. This gives us negative 3 root 6 over 4. So our tangent plane would be z is equal to negative square root of 6 over 4 plus the square root of 2 over 2 times x minus pi over 3 minus 3 square root of 6 over 4 times y minus pi over 4. So simplify this out. We'll have the square root of 2 over 2x minus 3 times the square root of 6 over 4y. And now let's get all of our constants. So 3 pi times square root of 6 all over 16 minus pi times the square root of 2 all over 2 minus the square root of 6 all over 4. And so we get as our tangent plane z is equal to the square root of 2 over 2x minus 3 times the square root of 6 over 4y plus 3 pi square root of 6 minus 8 pi square root of 2 minus 4 square root of 6 all over 16. We now look at the idea of differentiability. So we say that a function f of xy is differentiable at a point x0, y0 if for all points xy in a delta disk around P, we can write f of xy equals f of x0, y0 plus f sub x of x0, y0 times x minus x0 plus f sub y of x0, y0 times y minus y0 plus e of xy, where e is an error term and it satisfies this limit. So the limit as xy approaches x0, y0 of e of xy over the square root of x minus x0 quantity squared plus y minus y0 quantity squared is equal to 0. Now this error term represents how closely the tangent plane comes to the surface in a small neighborhood of the point. So what we're going to do is we're going to go ahead and show that this function, 2x squared minus 4y, is differentiable at the point 2, negative 3. All right, so first thing we're going to need is f sub x, and that is just 4x. And now we need f sub y, and that is negative 4. Now let's evaluate all of these. So f sub x, and f sub y at the point 2, negative 3. So f will be 20, f sub x will be 8, and f sub y is just negative 4. Now, f of 2, negative 3 plus f sub x, 2, negative 3 times x minus 2 plus f sub y of 2, negative 3 times y plus 3. This is going to equal 20 plus 8 times 2, times x minus 2 minus 4 times y plus 3. So we get 20 plus 8x minus 16 minus 4y minus 12. This is 8x minus 4y minus 8. So let's write this as 8x minus 4y minus 8 plus 2x squared minus 8x plus 8 is equal to 2x squared minus 4y, and this has to equal f of x comma y. Now this term right here is the error term. So what we have to do now is verify that this term satisfies the limit. So to do that, I'm going to move on to the next slide. So limit as x, y approaches to negative 3 of e to the x, y over that square root Remember, this had to equal 0. So this equals limit x, y approaches to negative 3 of 2x squared minus 8x minus 8 all over the square root of x minus 2 squared plus y plus 3 squared. Now this will equal the limit as xy approaches to negative 3, 2 times x minus 2 quantity squared all over the square root of x minus 2 squared plus y plus 3 squared. Now this will be less than or equal to this limit. And I'm not going to write the xy approaches to negative 3 anymore. 2 times x minus 2 squared plus y plus 3 squared all over that square root. And this will equal the limit of just simply 2 times the square root of x minus 2 squared plus y plus 3 squared. Right now here what we did was we said, oh, well, this is less than or equal to because I'm adding a positive term. Right, no matter what value y takes on, it's being squared, so squared is always positive. Now this has to equal 0. So if you plug in these points, that limit is 0. However, notice that e of xy is greater than or equal to 0 for all x and y. Well, there's only one value that is less than or equal to 0, and that's 0. So therefore the limit of e of xy over the square root of x minus 2 squared plus y plus 3 squared is equal to 0. That is the limit that needs to be satisfied, and so the proof is complete. And we'll close this video out by just looking at 2 properties. Now this definition can be used to prove them, but we're not actually going to go through the proof. So the first property, let z be a function of 2 variables, x and y, with p naught in the domain of f. If f of xy is differentiable at p naught, then f of xy is continuous at p naught. So just as in single variate, differentiability implies continuity. Let z equal f of xy be a function of 2 variables with p naught in the domain of f. If f of xy, f sub x of xy, and f sub y of xy all exist in the neighborhood of p naught and are continuous at p naught, then f of xy is differentiable at p naught. So this is a way to test for differentiability that does not require that long process we went through in the previous example. To show that it's differentiable, all we have to do is show that f, f sub x, and f sub y all exist and are continuous at p naught. Then we can say, oh, well, then the function must be differentiable at p naught. And so that will conclude our look at tangent planes.